Hello, children. This is your Kirti ma'am. And today we are going to see a very important topic. We are going to see all the reactions of alkanes, preparations, and its chemical reactions under the chapter hydrocarbons. So let's quickly start without wasting any time. First, we will see the preparation of alkanes. The first preparation of alkanes is we are going to add hydrogen molecule H2 molecule onto the double bond which alkene has. The first method of preparation is preparation from alkenes, all alkynes. You people know alkenes and alkanes are unsaturated compounds and alkanes are saturated compounds. So we are going to prepare saturated alkanes from unsaturated alkenes and alkanes. Further, what we will do, we will add hydrogen molecule onto the double bond. Okay, we'll add hydrogen molecule onto the double bond. To convert alkene into alkane, one hydrogen molecule is enough because we have to remove only one pi bond. But to reduce an alkane, okay, if you have to add hydrogen onto an alkane, I have to remove two pi bonds. So I need 2 moles of hydrogen here. So I need how many moles of hydrogen here? 2 moles of hydrogen. And whenever you observe here, okay, the addition of hydrogen happens from the same side. Okay, the addition of hydrogen happens from the same side. Okay, both the hydrogen atoms get attached on the same side. That is the reason which type of addition we call it as syn addition. Whenever the molecule gets added only from one side, we call it as syn addition. Clear? Now here we have a catalyst. You know what is a catalyst? Okay, it helps to change the rate of the reaction without itself getting consumed in the reaction. It will do its part. It will increase or decrease the rate of the reaction, but most of the time it increases the rate of the reaction and comes out of the reaction at the end. Okay, now here you people need to observe, because this is given in NCERT, platinum and palladium are used as catalysts at room temperature. If you want to use nickel, because we might prefer nickel because nickel is cheaper. So if you are using nickel, only thing you need to take care, because you have to maintain a higher temperature and pressure conditions, then you can use nickel. Clear? Now, when we talk about cis and trans alkenes, now you know what are cis and trans alkenes, you have studied in isomerism. Whenever I'm doing addition, okay, whenever I'm doing addition of hydrogen and cis on cis alkene, I get a meso compound. I get a meso compound. So always remember this thing. Okay, cis, if I'm doing, okay, cis plus syn addition, what does it give? It gives meso. Clear? Cis plus syn addition will give you meso. Cis plus syn addition will give you meso. Now this is your meso compound. Okay, check the plane of symmetry. Check the plane of symmetry, because you people know if it has to be meso, it has to be it should have a plane of symmetry. Now here, after addition of hydrogen, it has a plane of symmetry. That is the reason I call it as meso compound. If it is a cis alkene and I am doing syn addition, I get a meso compound. One more combination you need to remember: if it's a trans compound and I am doing syn addition, then I get a pair of enantiomers. Okay, you know what are enantiomers. Okay. Clear? Cis plus syn will give me meso. Trans plus syn will give me a pair of enantiomers. This is very important. You need to remember this for your exam. Now, next I can also prepare. Now we have seen preparation of alkanes from alkenes. Now let us see preparation of alkanes from alkyl halides. Okay, this reaction, if you see, you can take an alkyl halide. You cannot take a fluoride here for this. Okay, this doesn't work with fluoride. Take an alkyl halide, and what are the reagents I can use here? Okay, what are the reducing agents I can use here? Zinc in the presence of acid or base, I can use it as a reducing agent. So all of these are what? They are your reducing agents. I can use zinc plus acid or base, zinc in the plus HCl or zinc plus NaOH. You can also use lithium aluminum hydride. You can also use sodium borohydride, or very important, red phosphorus plus HI. Any reducing agent out of this, if you use, they can convert your alkyl halide into the respective alkane. This is not applicable only for fluoride. If you want the reason, you can check this bond is very much strong. Okay, the RF bond is very strong, means the carbon hydrogen bond is very strong here. So it is very difficult for the reducing agent to break this bond and reduce the alkyl fluoride. That is the reason, except fluoride, all of them can be reduced using all these reducing agents: zinc plus acid or base, lithium aluminum hydride, sodium borohydride, or red phosphorus plus HI. Using all these reagents, we can convert alkyl halides into respective alkanes. Now here a very important thing is that which you need to take care here. Primary alkyl halides. Okay, now I'll just tell you, sodium borohydride is a weak reducing agent. Okay, it is a weak reducing agent. Clear? Now, primary alkyl halides are less reactive. Okay, primary alkyl halides, first of all, are less reactive. On that, if you are using a weak reducing agent like sodium borohydride, there will be no reaction. Please remember. Okay, now tertiary alkyl halide is very much reactive, and lithium aluminum hydride also is a very strong reducing agent. Okay, that is the reason strong, both of them are very strong. So what happens? The reaction will be very strong, and you don't get an alkane, you get an alkene. Okay, instead of acting as a instead of acting as a reducing agent, what does lithium aluminum hydride do? It converts the total alkyl hydride to alkane. So these two things are mentioned in NCERT, so please remember. Now, if I go for the next reaction, this reaction you study even in the chapter aldehydes and ketones in grade 12. If I take no if I take like any carbonyl compound, okay, you can take aldehyde or you can take a ketone, that is your choice. You can take aldehyde or ketone. Aldehyde or ketone, if you take and use this particular reducing agent, okay, when you use zinc amalgam in the presence of HCl, I call it as Clemenson's reduction. Okay, this you study this named reactions. Okay, even in the chapter aldehydes, ketones, and carboxylic acids. Okay, when you are this is Clemenson's reduction, and whenever you are using N2H4, N2H4 is called hydrazine. Okay, N2H4 is called hydrazine. Whenever you are using a hydrazine in basic condition, okay, you have both these reactions. Okay, you have in acidic condition and you have in basic condition. Whenever you are doing the reaction in basic condition, you call it as Wolff-Kishner reduction. Okay, Wolff-Kishner reduction. If you are using zinc amalgam in the presence of HCl, it is Clemenson's reduction. If you are using hydrogen in the presence of base, I call it as Wolff-Kishner reduction. Okay, when you use this, what happens? This carbonyl group, whatever carbonyl group is there, it is getting converted to or it is getting reduced to which group? Your CH2 group. Okay, whenever you are using a reducing agent, this carbonyl group will get converted to CH2 group and you get the respective alkane. Clear? Okay, now what you have to take care is if in the carbonyl compound, an acid sensitive group is there. Like for example, OH, alcohol is an acid sensitive group. Okay, alcohol is an acid sensitive group. If in the carbonyl group, along with the carbonyl group, you also have an acid sensitive group, then please don't go for Clemenson's reduction. If acid sensitive groups are there, don't go for Clemenson's reduction. What is the best example of acid sensitive group? It is OH. What happens is from this acid, H plus will come and it will react with this and form OH2. Okay, and form OH2, positive charge on oxygen, and this will go as this will get eliminated as water, and you get a carbocation over here which goes to a completely different reaction. So what is the problem? If you take an acid sensitive group and doing Clemenson's reduction, the H plus from the HCl comes and reacts with OH, and it will leave as okay water molecule because it's a good living group. That is the reason Clemenson, if acid sensitive group is there, don't go for Clemenson's reduction, instead go for Wolff-Kishner reduction. Now you cannot use Wolff-Kishner reductions when you have base sensitive groups. Okay, what are your base sensitive groups? Okay, what are your when shouldn't I use Wolff-Kishner reduction? If I have base sensitive groups. What are your base sensitive groups? It is your ester. If ester is there, if you have along with carbonyl compound and ester in the compound, if esters no, okay, ester is a base sensitive group. Base will go and do hydrolysis of ester. Okay, base, you people know this, base will go and do hydrolysis of ester, and that will that will interfere with it. Okay, so please don't use a Wolff-Kishner if base sensitive. Ester is a base sensitive group. Ester is a base sensitive group. Your halogens also are sometimes base sensitive groups. Okay, halogens are sometimes your base sensitive groups. Okay, and amines. Okay, amines are also base sensitive groups. What happens if base is there? The base will go and react with amine group. Okay, that is the reason whenever you have base sensitive groups like ester, halogen, and amine group, please go with Clemenson's reduction. Whenever you have acid sensitive group like alcohol in the compound, go for Wolff-Kishner reduction. I hope all the reactions are clear for you till here. Yes. Okay, these reactions keep repeating in various chapters. So if you're learning it for one chapter, it is definitely useful for your other chapter. Now let us see the next preparations. Okay, let us focus on the next preparations. What are the next preparations I have? Let us quickly do. Okay, let us quickly do the next preparations here. Okay, what is the next preparation? Okay, here what am I doing? Again, it's some alkyl halide. From alkyl halide, we have already seen Clemenson's reduction and Wolff-Kishner reduction, and we have also seen reduction of alkyl halides using different reducing agents. Now again, I'm using alkyl halide. See, you have many preparation methods from alkyl halides. First is the reduction part. Next also is reduction, Clemenson's and Wolff-Kishner. Now what am I doing? I'm taking an alkyl halide and I'm treating it with magnesium and ether. Okay, magnesium and ether. Then what do you get? You get RMgX. Okay, what do you call this RMGX as, we call it as Grignard reagent. Now, when I want to mention you a little bit about Grignard reagent, okay, Grignard reagent, in Grignard reagent, this is a very rare case where your alkyl group has partial negative charge. Usually alkyl groups hold partial positive charge, but in Grignard reagent, your alkyl group holds a negative charge. Now, these alkyl groups can act as both base and a nucleophile. This alkyl group can all act as both base and nucleophile. When alkyl group is acting as a base, okay, when alkyl group is acting as a base, what is the role of a base? Base will abstract a proton. Okay, base will abstract a proton. Clear? So in this reaction, your Grignard reagent is acting as a base, and it will abstract proton. Now Z can be anything. Now, which compounds have a acidic proton? Which compounds have a acidic proton? You can take CH3COOH. Okay, in this is the acidic proton. Acids have acidic protons. There are some compounds also which have acidic protons. Okay, you have HCl. In HCl, H is your acidic proton. You know, all mineral acids have acidic protons. You know, all weak acids also have, all weak organic acids also have acidic protons. Apart from this, from that, even in alcohol, this is an acidic proton. Even in phenol, this hydrogen is an acidic proton. Even when you take an alkyne, even in alkane, the terminal alkyne, this terminal hydrogens, okay, the terminal hydrogens are, okay, are acidic hydrogens. Now, whenever your Grignard reagent comes across with these kind of compounds, whenever your Grignard reagent comes in contact with these kinds of compounds, it will abstract the proton. Okay, it will abstract this proton, and this Z can be anything. Okay, and this Z can be this CH3COO, this Z can be your chlorine, this Z can be your RO, Z can be anything. But the only condition, the compound should have an acidic proton. This Grignard reagent will abstract the acidic proton, and it will form the respective alkane. So RMGX, Grignard reagent, abstract acidic proton from the molecule. Clear with this? So from alkyl halides, I have taught you three types of reactions. From alkenes, I have taught you the reactions. Okay, so from alkenes and alkanes, we have done reduction using hydrogen. Clear? Now, from alkyl halides, we have one more very important reaction, which is your Woods reaction. Very important reaction. In Woods reaction, you will take 2 moles of alkyl halides. Okay, 2 moles of alkyl halides. In fact, similar alkyl halides. Similar. If you are taking CH3X here, you will take CH3X here. If you are taking if you are taking ethyl halide here, you will take ethyl halide here. So you will take similar type of alkyl halides, and you do Woods reaction. What exactly happens from this? Okay, you react both the alkyl halides with sodium. Okay, sodium goes with these 2 halogens. Okay, and what am I left with? Am I left with an alkane? Okay, I'm left with an alkane. This alkyl group and this alkyl group combine and form the respective alkane, and I do this reaction in the presence of dry ether, and you also get here, what do you get here? I get here plus 2 NaX and my respective alkane. Okay, now obviously it will give even number of carbons. You get only alkanes with even number of carbons, right? Yes, because you are taking similar alkanes. Here, if you are taking CH3Cl, here you will take CH3Cl. Then you get ethane. Here, if you are taking CH3CH2Cl, here also you will take CH3CH2Cl, and then you get butane. Now you might be getting a doubt. Okay, now you might be getting a doubt here. Ma'am, what if I take CH3Cl here plus CH3CH2 plus CH3CH2Cl, means different kinds of alkyl halides. Okay, then will I not get CH3CH2CH3, and this alkane has odd number of carbons? You should be getting that doubt. You can do this reaction. That's not a thing. You will definitely get a propane, but the disadvantage of this is, now there is probability that there is every chance this methyl chloride again reacts with other methyl chloride and give me ethane. Right, there is other possibility also, this ethyl chloride reacts with other ethyl chloride, okay, and give me butane. Now here the selectivity is reducing, right? You are aiming at one type of compound. Okay, you are aiming at propane, which is your selected compound which you want, but I'm getting all unnecessary things also. We don't do any reaction to get multiple products, right? We do reactions to get a specific product. Now here, if you are doing with 2 different alkyl halides, you are getting different products, okay, which is reducing the selectivity of the reaction. Okay, that is the reason we usually take similar alkyl halides, so you get a given alkanes come with even number of carbon atoms. If you are taking different alkyl halides, what is happening? You are getting a mixture of alkanes. Hope this is clear. You are getting a mixture of alkanes. Okay, next one. Okay, next one is a very important reaction. Okay, next one is a very important reaction. What are we going to do? In the next reaction, we are going to learn about our Coles electrolysis. Okay, we are going to learn about our Coles electrolysis. Before that, we will do what? Decarboxylation. The next reaction for the preparation of this is decarboxylation of carboxylic acid using soda lime. Okay, we are using soda lime and we are doing the decarboxylation. See here. Uh, okay, I think we have missed the reaction above. Just give me a second. Yeah, this reaction is Bohr-Woods reaction. If we go to the top, 1 second. Yeah, I think we have missed it in between, right? Yes, we did Grignard and then we did Wood's reaction. In between, we have missed the preparation from carboxylic acids. Yes. Okay, there is one more reaction in between. We can even prepare our alkanes from carboxylic acid. How are you going to prepare alkanes from carboxylic acids? We are going to use NaOH in the presence of calcium oxide. Now, NaOH and calcium oxide plus heating. Okay. What is the role of that? This we call it as soda lime. Okay, what do you call the combination of NaOH plus CO and heating? We call it as soda lime. Okay, we call NaOH plus, please remember, NaOH plus calcium oxide. What do we call it as? We call it as soda lime. If you are thinking how did this name come, you know CaO is called quicklime. Okay, and you know NaOH, you know, you call it as soda. Okay, that is the reason you call it as caustic soda. That is the reason together we call it as soda lime. And what is the role of this soda lime? It will do what? What is the role of soda lime? It can do decarboxylation. The role of soda lime is it can do decarboxylation. Clear? Okay, now what happens when I take this soda lime and I heat it? It does decarboxylation. So what will go from the molecule? CO2 is lost from the molecule. Okay, CO2 is lost and this CO2 will go and react with, okay, this CO2 will go and react with this soda lime part. Okay, with this soda lime part. And basically, I'll tell you something. The CO2 which is going from the molecule, what it will do? It will interact with your NaOH. It will react with your NaOH and giving sodium carbonate. Giving sodium carbonate. This CO2 will leave the molecule, interact with sodium hydroxide, giving sodium carbonate. Okay. Now what happens here when CO2 goes? What is remained in the molecule? RCH3. That you write it as a product. So any carboxylic acid they might give. For example, if they give you propanoic acid. Okay. If they give you CH3, CH2, COOH, and if you are doing if you see in the reaction you have soda lime comma heating, so what you will do, you will remove this CO2 and what will be your product here? Your product will be ethane here. Okay, your product will be ethane here. So this is how you write the products. And plus by default Na2CO3 is always there. So any carboxylic acid they give, eliminate the CO2 and write the product. So this is your soda lime decarboxylation, where you use carboxylic acids to prepare the respective alkanes. Hope this is clear. Now we have come to the last preparation method, which is my Coles electrolysis. In Coles, see, from carboxylic acids, you have two methods of preparation. Okay, two methods. One is using soda lime, which does decarboxylation, and one more thing we are going to do from carboxylic acids is your what? Coles electrolysis. In Coles electrolysis, we treat the acid with KOH. You know, no base will abstract the proton, and what will happen here? For me, a salt is formed. A salt is formed. This is your potassium salt of carboxylic acid. What is this? Potassium salt of carboxylic acid, because this OH has abstracted the proton and potassium has come and attached to this part. I got my sodium salt of carboxylic acid. Now I will do the electrolysis of sodium salt of carboxylic acid. How will you get the product? This is very easy. Whatever R is there, okay, for example, if you are using CH3COOK, this is potassium salt of ethanoic acid. Now from this, what do you get? From this, take this methyl, okay, and add one more methyl. Okay, and add one more methyl. Okay, just double it. So what will be your alkane product here? You will get ethane from here. Okay, whatever R group is there, just put one more R group. So you will get R dash R. So here it is my ethane. Plus from here, what will happen from the all other things present in the reaction? What are the side products you get? You get your carbon dioxide, and these two products are obtained at anode. And at the cathode, what is remaining? What is left in the solution? Okay, at cathode, what do you get? At cathode, you get your hydrogen gas, and NaOH is present in the solution. So at anode, what, very important question, at anode, what do you get? At anode, you get your alkane, and at anode, you also get your CO2. At cathode, you get your hydrogen gas, and in the solution, what is there? NaOH is there. Okay, so this is a very important reaction in Coles electrolysis. Now, how to write the products of Coles electrolysis if given in the exam? Just what did I ask you people to do? Remove this CO2. Okay, if you remove this CO2, what is left here? Okay, this actually happens through free radical mechanism. This reaction actually happens through free radical mechanism. If I remove CO2, here I will get a radical. What did I told you? Take one more alkyl radical like this, okay, and attach these two parts. Attach these two parts. You get two R groups. The same thing you do here. Okay, the same thing you do here. I will break this. Okay, okay. I will here what I have to do. Here I have a dicarboxylic acid. Here I have a dicarboxylic acid. So what do I do here? Whenever I have a dicarboxylic acid, let me do again. Okay, what did I ask you people to do? What did I ask you people to do? Remove this CO2 here, remove this CO2 here. Here I removed one CO2. See, here when I removed CO2, I got it like this, no radical. I took one more radical and I have joined them. And I have joined them. Do the same thing here. It is a dicarboxylic acid. Break here, break here. CO2 will go. Then what do I get here? R, CH. This is R prime, CH. Okay. Now here, because this bond has been broken, here already one bond is there, because this bond has been broken, I will get a radical here, because here one bond has here CO2 bond has been broken with carbon. I'll get one more radical. These both radicals will combine. What do I get here? RCH. Okay. Okay, you can get an alkene here. You can get an alkene. Whenever you are taking dicarboxylic acid and doing Coles electrolysis, what you get? You can get an alkene. The same thing, okay, the same thing you apply here. Okay, already double bond is there. Okay, this bond will break, this bond will break. I'll get a radical there. C, double bond, C, R prime. I have got radical here. Both the electrons, both the single electrons will combine, and I get C triple bond C, R prime. Okay, if it is monocarboxylic acid, nothing. Create one radical here, one more the same radical you put here. Okay. Yes, so this is the way you do the Coles electrolysis, and you can write the Coles electrolysis products in this way. Okay, if it is single carboxylic acid, just make two radicals of the same alkyl group, and you just need to attach the radicals part. Clear? Now this is all about the preparations of your alkenes. Now let us try to go and understand the reactions of alkenes. Okay, so what are the preparation methods we have seen for alkanes here? What are the preparation methods we have seen from alkanes? We have seen the preparation of alkanes from alkenes, and we have done the reduction of alkenes and alkynes. Then I got my alkane. Then we have done what? Then we have done, then we have taken alkyl halides and done reduction of alkyl halides using various reducing agents giving alkane. Then we have taken carbonyl compounds, have done reduction of carbonyl compounds using Clemenson's reduction and Wurtz-Fishner reduction. Then I got an alkane. Then I have taken alkyl halide, and made it into Grignard reagent. Then this Grignard reagent abstracted the acidic proton, and then we got an alkane. Then we have taken carboxylic acid. With carboxylic acid, I can do two types of reactions. I can do decarboxylation of carboxylic acid giving alkane and sodium carbonate. Okay, with carboxylic acid, I can also do Coles electrolysis with alkane and carbon dioxide getting released at anode and hydrogen gas released at cathode. Then we have Woods reaction, which will do taking alkyl halides reacting with sodium in the presence of dry ether. Clear? So these are all about the preparations of alkanes. Now let us go and see the reactions of alkanes. Okay, let us do reactions of alkanes. Now, in the reactions of alkanes, the first very important reaction of alkanes is my halogenation reaction. The first very important one is your halogenation reaction. Okay, you will take an alkane and do halogenation in the presence of sunlight or UV light. When you do that, what happens here? Okay, the halogen, okay, whatever halogen you have, it gets attached to your alkyl group. Okay, gets attached to your alkyl, and all this process will take place through a free radical mechanism. All this process takes, whenever you take UV light or sunlight, usually the mechanism is free radical mechanism, because whenever you use UV light or sunlight, what exactly happens? Homolytic fusion of the bonds takes place. Homolytic fusion of the bond take place, giving you free radicals. Now here you can do with any halogen. If you see the reactivity of halogens for this reaction, how enthusiastic are the halogens to react with alkane? Fluorine, obviously, then chlorine, then bromine, then iodine. This is your reactivity with respect to your halogens towards halogenation. Now, this is your reactivity with respect to your, with respect to your alkanes. Okay, clear? Okay, now let us do, okay, now let us do this. We will take an alkane. Okay, we will take an alkane. And what are we going to do? We are going to do halogenation in the presence of sunlight. Okay, in the presence of sunlight. Now you see the difference. Okay, why are we not doing chlorination here? I'll tell you that. First, let us see chlorination and bromination. Chlorination reaction is very fast and reactive. Because chlorination reaction is very fast and reactive, okay, it will not see if it is attacking on a primary carbon. Okay, if you see, this is your primary carbon and this is your secondary carbon, right? Okay, if you see here, this is your, what type of carbon is this? This is your, this is your primary carbon. This is your primary carbon, and this is your secondary carbon. Whenever the carbon, okay, when you know how do you detect the primary carbon and secondary carbon? Whenever the carbon is attached to one carbon, we call it as primary carbon. Whenever the carbon is attached to two carbons, we call it as secondary carbon. Clear? Now here if you see, attack of chlorine is very fast and very reactive. It is not selective. Okay, it will see, you people know. Okay, secondary free radical is more stable than primary free radical. But chlorine, because it is very reactive, it doesn't see, it doesn't differentiate whether it is attacking on a primary free radical or secondary free radical. It just attacks. It is very fast and it is not selective. It attacks equally on primary free radical. It attacks equally on secondary free radical. That is the reason you get a primary alkyl halide and a secondary alkyl halide in the ratio of 1:1. When you go to bromination, bromination reaction is very slow and selective. Okay, bromination reaction is very slow and selective. Because bromination reaction is very slow and selective, what happens? You get more percentage of your secondary alkyl halide. Okay, secondary alkyl halide, because here you people know, here the free radical will be the secondary free radical, which is more stable. That is the reason bromine goes and preferably attacks at the secondary position, giving more percentage of your secondary alkyl halide and less percentage of your primary alkyl halide. Clear with this? So please see the difference. Now when we go with the fluorination part, fluorination is too violent to be controlled. That because it is violent and we can't control it, we usually avoid doing fluorination. Why do you have to do the reaction and get into trouble? So we don't usually do fluorination reaction. And the problem with iodination reaction is it is a reversible reaction. If you see here, okay, methane plus iodine gave methyl iodide or iodomethane plus HI. Now what happens is this HI is a very good reducing agent. This HI is a very good reducing agent. So what will happen? Okay, what will happen here? I'll tell you what will happen. This HI is a very good reducing agent, so it will want to undergo oxidation. Okay, it will want to undergo oxidation, so it will want to release hydrogen from itself and go back to iodine. So immediately as soon as HI is formed, because it is a very good reducing agent, it wants to undergo oxidation. It will go reverse and give back it wants to go reverse and give back iodine. Okay, but we don't want it. No, we want the reaction to go forward. We want the reaction to go forward and we want to get methyl iodide or CH3I. But HI is immediately want to go backward because it is a reducing agent, good reducing agent. It wants to become iodine and so it wants to go reverse. So in order to solve this problem, what we have to do, we should use a strong oxidizing agent to control a strong reducing agent. Now, if you are using a strong no, oxidizing agent, okay, like HNO3 or HiO3, because they are very good reducing oxidizing agents, immediately as soon as HI is formed, what they'll take HI. They'll take HI. HiO3 will react with HI and forming iodine plus H2O. So immediately as soon as HI is formed, the oxidizing agent will act on the reducing agent and take it with it and convert it into iodine separately, so that the reaction will not go in a reverse direction. So iodination is reversible because HI is a very strong reducing agent. It undergoes oxidation and wants to come back as iodine. So the backward reaction is equally possible. That is the reason we use a strong oxidizing agents like HNO3 and HiO3, so that it takes that HI and convert it into respective iodine. Clear? Okay, one second. Okay, now we will do the next reaction. Okay, now let's do the next reaction. What is the next reaction here? Next reaction is our, okay, I have to explain you one more part here. Now in exam usually they give this kind of questions. In exam they usually give this kind of question. For example, if you see here, this is my 2-methyl butane. Okay, they'll give you a compound and ask you how many types of products are formed. When you have to tell how many types of products are formed, you have to check how many unique positions of carbon are there. Okay, now if you see here, okay, this carbon is one type of carbon, this carbon is other type of carbon. Okay, this carbon is other type of carbon. Okay, and this carbon is other type of carbon. Now this carbon I won't take because this carbon and this carbon are in the same atmosphere, so this is not unique. Okay, this carbon is the same type of carbon as this is. So how many unique positions of unique types of carbons I have? This is one carbon, this is other carbon, this is other carbon, this is other carbon. You have to check in which atmosphere is the carbon there. This carbon is in a different atmosphere compared to this. This carbon is in a different atmosphere compared to this, and this carbon is in a different atmosphere compared to this. But these two carbons are in the same atmosphere, so I will not take this carbon as a unique carbon. Take one of them. Okay, so I have four unique positions, so I'll get four different products. So wherever you have the unique carbon, on that position you put your Cl. Okay, remove hydrogen and put Cl. Okay, but be careful. If you have any chiral carbon, okay, if you have any chiral carbon, then please think. Okay, for example, okay, if you have any chiral carbon, then what happens? For example, if you have something like this, okay, if you have something like this, okay, if you have a compound like this, okay, now this is your chiral carbon, this is your carbon, right? This is your chiral carbon. Okay, now you will count the unique carbons that is there. You will count the unique carbons that is there, and you will write the four different products. But when you are writing for this compound, okay, when you are writing the writing the product for this compound, because it has a chiral carbon, you have to take the stereoisomers of that, because it is an optically active compound. It is an active compound. You get both D and L. So please take care of that. Okay, if in the products, okay, if you have a chiral carbon, that will give stereoisomers, right? Okay, D and L it will give. So please count both. Please count the stereoisomers in that case. If it doesn't have chiral carbon, you can count it individually. But if it has a chiral carbon, it will give stereoisomers. So please count the stereoisomers also in case in the products, if you are having a chiral carbon, please take care of that. Okay, usually we ignore that. So kindly don't ignore that fact. Okay, now the next part. Okay, now the next part is what? Okay, now the next part here will be, okay, let me clear the drawings here. Okay, the last one, isomerism, and I know isomerization and aromatization. Okay, you try by yourself. If you are not getting it, I'll explain you in the next class. But before that, what is the thing we are going to do here? We are going to do the controlled oxidation. Okay, you try isomerization and aromatization. I want you to check in NCERT and try these reactions. If you are not trying it, when I do the alkenes video, I'll explain this at the end. I'm giving it as a homework for you people to try isomerization and aromatization because they are very easy. Okay, still you try. If you don't get, I'll explain you in my next session at the end of alkanes, isomerization and aromatization. Now, controlled oxidation when you are doing, okay, you don't do freely the oxidation. You will control the oxidation, and you can control the oxidation by using different reagents, because different reagents have different capability of doing the oxidation. Now, methane plus oxygen in the presence of copper you are doing, then you get methanol. The same methane plus oxygen, if you are doing in the presence of molybdenum oxide, it will give you a formaldehyde or methanol. Okay, the same controlled oxidation, if you are doing in the presence of manganese acetate. Okay, then the first case I have taken copper as the oxidizing agent. In the second case, I have taken molybdenum oxide as the oxidizing agent. In the third case, I have taken manganese acetate as the oxidizing agent. Okay, in the fourth case, I have taken KMnO4 as an oxidizing agent. Now you see the difference. When copper is taken as an oxidizing agent, I got methanol. When molybdenum oxide is taken, I got my methanal. Okay, methanol, which is also commonly called as formaldehyde. When I have taken manganese acetate, I got my ethanoic acid. When I have taken KMnO4, I got my alcohol. So this is how I can change my product based on the oxidizing agent I am taking by controlling the oxidation. Now please try isomerization and aromatization. In case if you are not doing it or you are not getting it, I'll do it at the end of my next video, which is on alkenes. So don't mix my next session, which is completely on alkenes. Till then, please studying, do follow my videos. In the next session, I will be doing the reactions of alkenes, if possible alkanes too, but okay, let's keep it confined to alkanes. Till then, this is Kirti ma'am saying bye bye. Please watch our sessions, share our sessions. I'll see you in the next session. Bye.